Lesson 17, and here is the cover page. Actually, the photograph is important. So today's topic is level pool routing, and what level pool routing is one of the hydrologic routing techniques. And I chose this photograph on purpose. This is in Northern California. Those mountains in the back are the Trinity Alps. And this is Lake Shasta, and this is the dam that impounds Lake Shasta. So the difference from this parapet, or this tower, back over there to the edge of the horizon is several miles. And so any flow coming off of these mountains into this lake, which is our level pool, is going to take time to traverse from this location out to the dam. And level pool routing is one of the routing technologies that's used to explain that flow. And essentially we're following Chapter 8 of Chow Mei May's lumped system routing. And in particular, these graphs should look very familiar from last time's meeting, and we're going to follow section 8.2, and I'm pretty sure the numerical example I use is taken directly from section 8.2. Here's our storage equation, some graphs to explain it, outflow controls, which we'll get to shortly, and the example that we use. Okay, with that having been said, I want to return to yesterday's example that I was working on and completed. So I'll get that connected and running, and then I'll actually pull up Okay, good. I left it running unchanged. So here was where we left off yesterday. We had built a HEC HMS model with 3 different subbasins, green, blue, and red. And red connected directly to our outlet, which I've given the name composite. I suppose I could rename that to outlet. And green, the outflow from green traverses a routing element indicated by this large or this thick blue line to the outlet. And the outflow from the blue subbasin traverses this routing element to its composite. And that's where we left off last time. So nothing's been parameterized yet. So we will return to yesterday's example and bring it up. Do my rapid fix. Get 16. Oh, rats. I don't have a PDF, so I actually have to download it and open it. And because of the high-speed internet, it's going to take a while. That's not bad. We're getting a couple megabytes a second. No, half a megabyte a second. even though my contract with the internet service provider is supposed to be 10 megabytes a second. Turns out the high-tech industry can't count. Okay, there's my usual griping. It's done, and we have our example. And I wanted to get down to about there. And we were working through the second part of the example where it had multiple subbasins. I thought it did. I bet I just downloaded the wrong example. No, okay, there we go. Multiple subbasins, red, green, and blue. And the green goes from its outlet to the main outlet. The blue goes from its outlet to the main outlet. And the red watershed directly connects to the main outlet. And so this is a pictorial diagram of what's going on. There's the green. So the thick blue line in the Heck HMS model is the element that takes care of this green arrow. And same for the blue watershed. There's an element that deals with that blue arrow. And I believe we got as far as this. We were able to get the areas of the red watershed, the green watershed, and the distance from the green watershed to the outlet. And we'll see if that's immediately relevant. The blue watershed's area and the distance from the blue watershed to the outlet. And we can summarize this information. The areas add up to within 1% of what they should. And the outlet distances are listed here, and the 3 curve numbers are listed here. And that's the methods that we'll use in this example. So along the 2 distances to the outlet, we'd need an estimate of slope. And if we wanted to keep the example brief, we could use the main channel slope as the estimate and apply it to all the slopes in the watershed. That's not a perfect decision, but it will do for the case at hand. And so the dimensionless slope is 0.0056. And now we need to estimate the routing information. This example was lag routing, so all we need is a travel time from each subbasin to the main outlet. To get that travel time, we go to the literature, and there's a variety of approaches. One of them is documented in this report, 4695-2, that was prepared for the Texas Department of Transportation. And in that is a pair of relatively simple to apply formulas that simply need a path length and a slope to estimate time. And here we'll just directly apply the formulas, and we get lag times of 37 and 26 minutes for the green to outlet and blue to outlet, respectively. So now we can continue with our model example. Let's keep that handy because I think I'm going to need it. So this is the blue to the outlet, and we need to give it a lag time in minutes. And this one says 26 minutes would be our choice. So that's entered. And this one, which is green to the outlet, is 37 minutes. So we've now provided our lag information, and Basin 1 contains elements. Oh, that's just a warning. I'm not going to worry about that. So we've built the model, and we need to provide basin lag times for the subwatersheds as well as the curve numbers. And that's up here in our estimates. The three basins are all going to be supplied with a curve number of 86. Let's go here and do that. So we need a loss method. Loss method will be curve number. And transform method is going to be SCS hydrograph. And now we need to parameterize it. So the curve number is 86. We'll leave initial abstraction blank for the time being. Transform is, we've already done the arithmetic for that, so we'll just copy it from here. Green is 49 minutes. Now we need to move to blue. Curve number. Transform. Parameterize it. Blue is 46 minutes. Lastly, let's see, green, blue, and the red watershed. Curve number. Transform. Parameterize them. See, we're in red, 41 minutes. So the watersheds are parameterized and the lag times have been established. Let's verify the meteorological model is set up correctly. So everybody is going to get, I think, gauge 2. Yep, everyone gets gauge 2. That's done. And we're going to make another quick check. Be sure the basins are all turned to yes. Good. And I don't think there's any other funny business. And we will put the observed flow at the junction. All right, so that should complete our model. So quick description. The topology on this left side is modeling the Ash Creek watershed. The topology over here, Ash Creek is a whole basin, is where the hydrology is applied to the entire basin as a single element. So we would anticipate some different results, but the general patterns we would expect to be the same, assuming I have Ash Creek whole basin parameterized about the same way. We'll make a quick check of that. And they're not parameterized the same way. Let's switch that to curve number so we're comparing the same thing. Okay, so now they are identical models. Complicated, simplified. Let's run it and hope I don't get too many error messages. Oh, that's really cool. It actually ran. And now we're going to look at the output here for the composite. And what we see is the solid blue line represents the composite outflow, and then the black line with the dots is the observed flow. We don't have our loss model very well calibrated to the observations. And then these other ones are the inflows coming from the different watersheds. One of them is red, one of them is green, one of them is blue. If we were to look at the same output for the Ash Creek whole basin, I believe the diagram has quite a bit of similarity, although it's representing, come on, there you go. Trying to show them side by side. And it's not behaving. Hopefully the resize was captured. Okay, picture on the right is the whole basin case. The picture on the left is the 3 sub-basin case. And the important trace is this composite hydrograph. They look identical. I don't think they are identical, but they're going to be close. So the peak here is 6,000. The peak here is a little over 6,000. And the point of that was to illustrate how we can break a watershed into pieces and replace lumped components with, in this instance, routing elements. So I will leave that there for the time being and return to level pool routing, which is one of the lumped routing techniques. So the routing technique that was just illustrated in the simulation was lag routing. In other words, the hydrographs move from point A to point B, and the hydrograph at point B is identical to point A, but it occurs at a different time. And that time's the lag time. So in level pool routing, that's the same as before. We're looking at this second item, modified pools. And we've seen this diagram before. So what we're going to be explaining is the inflow, the outflow, and how that affects storage changes with time. So in level pool routing, it's a technique to approximate the outflow hydrograph passing through a reservoir. And the reservoir could be a a portion of a stream, a reservoir as is pictured in the first picture, or a detention basin, any element where you can either justify or are willing to justify that the water surface elevation is always level. It's an approximation, but it's a good one. And it uses a mass balance equation written here. Discharge in minus discharge out equals the change in storage with respect to time over a time interval of length delta t. Additionally, there's a storage outflow relationship which states that the discharge out of the element is some function of the current storage in the element. And we'll have a sketch to depict that in a second. Somebody just disconnected unintentionally. In this, the variable names are usually changed to I and O for inflow and outflow. And the reach mass balance is then expressed as the time average of inflow minus the time average of outflow is the change in storage. These time average values are taken at the beginning and end of a time interval, and the time interval has to be pretty short. So delta t being a year long doesn't make a whole lot of sense for routing calculations. But delta t being a day or 2 days or maybe a week, that might have some validity. And the first order difference quotient is used to approximate the rate of change of storage. So the inflow at time t plus the inflow at time t minus delta t. So think of the current inflow plus the prior inflow divided by 2. So that's an average inflow over a time period of delta t minus the current outflow plus the prior outflow also divided by 2. So an average outflow over that time period delta t is equal to the change in storage in the reservoir, S sub t minus S sub t minus delta t. If we rearrange that mass balance equation, we can isolate the storage and the outflow at the end of the time step. So this sketch here is depicting the reservoir in elevation view or side view. So there's inflow at one end, outflow at the other end, and the shape of it, in this case, is just a drawing. Storage is somehow related to how deep the water is. So average inflow is taken at this end. Average outflow, we'll assume for the time being we calculated at that end. And we can rearrange the equation so that storage is set on the right-hand side of that equation. Then we rearrange it some more so that we can set storage. This one here, and here, and here, that's just representing the prior time step. Probably should be t minus delta t and t. So there's a notation mistake here. So here's our inflow and outflow, and we've taken that outflow term that was in this square bracket, moved it to the right-hand side at time level t, and we've taken the storage term that was at t minus delta t that was on the right-hand side and moved it back to the left-hand side. And so there's what our storage equation looks like at this moment of the arrangement. Then we do a little more algebra and group terms. So this square bracket is the average inflow. This square bracket is twice the storage at the old time level divided by the time step length delta t minus the old outflow, which is equal to twice the storage at the new time level divided by the time step length plus the outflow at the new time level, And the right-hand side is essentially going to be unknown, but there's some shenanigans we can play with algebra to help us out. And so in the upper equation in this diagram, it contains two unknowns, which is the storage at the new time level and the outflow at the new time level. And that's where this storage outflow function, outflow is some function storage, comes into play. That outflow function can be the result of a lot of different hydraulic elements, such as flow over a weir, critical flow in a known geometry, flow through a outlet pipe, and so on. And if there's a big snowstorm, it looks like that. And so now we're going to keep those relationships in mind, and now use this motivating diagram. Let's suppose that the outflow can be flow over the top of the dam as some kind of weir, or flow in an orifice through some kind of hole. And we're using a dam here, but it can be any physical structure that exists in the flow regime that causes ponding behind it. And we're going to use the depth in the reservoir as our state variable that tells us how much storage there is. So the depth times a depth area function would tell us the total amount of storage. And the inflow is coming here from the left. So a couple of statements. Storage is proportional to depth, so we'll have storage is some function of the depth. And we have outflow is proportional to depth. So Q is some function of depth. In this diagram here, those functions aren't necessarily the same function. But we can relate storage and outflow into a storage outflow function. So if the flow happens to be over a weir, we can apply some weir equation. And in this diagram here, there's the inflow coming in, it's forming some ponding, and then there's flow over the weir, and the weir flow in this particular case is some weir coefficient multiplied by the length of the weir. A weir length would be in this dimension, transverse to those arrows, multiplied by some storage depth raised to the 3/2 power. So that's a pretty classic weir flow equation. Essentially it's an energy conservation statement. We could have flow through an orifice, a culvert, or similar structures. And in those cases, the discharge is some coefficient multiplied by the square root of 2gh, where h is the depth above the center line of the orifice, at least in the usual method. And that's typically an energy loss model. And we use that information, whatever the outlet works hydraulics are, and depth area storage to build that storage outflow function. And we'll stipulate here that outflow is a function of storage, that if you possess the geometry and the hydraulic outlet works in simple elements, that function is buildable. That can be determined entirely from geometry. Once we have the function, then we can build an auxiliary function that's called the storage indication curve. And it too is a function. And the storage indication curve relates outflow to some function of the current storage with respect to time plus the current outflow. And that storage indication curve is sometimes called is part of something called the routing table. Once we have the storage indication curve, then we can use the reach mass balance to estimate the numerical values of 2 times the current storage over the time step plus the outflow in the current time. And then with the use of the storage indication curve, we can find the value of outflow, subtract it from the result above, and now we have both the end of interval outflow and storage, and which is the whole point. So if we were to look at Chow Mabit Mays, pages 247 to 252, which are right there, these are the discharge equations that are presented in the book, and we're going to do essentially example 8.2.1. So let me read it. A reservoir for detaining flood flows is 1 acre, has a 5-foot diameter outlet pipe, and the headwater discharge relation for the outlet pipe is given in columns 1 and 2 of the table. So for a given depth in the pond, anywhere from 0 to 10 feet, the outflow through that pipe goes from 0 up to 275 cubic feet per second. And here's a sketch of what's depicted in that table. So 1 acre basin, vertical walls, drained by a 5-foot diameter reinforced concrete pipe. And in the example, the maximum depth is set to 12 feet. I've added some additional information with an outlet slope of 3 parts in 1,000, a Manning's end for the pipe of 0.013, and a discharge coefficient of 0.574. The reason we would do that is that's the kind of information necessary to construct this discharge function. Here in their example, it's done for us, but in practice, that would be something that we the hydrologists, would have to do ourselves. So our task would be to build a depth storage table and a depth outflow table. And I have some additional information here that from 0 to 5 feet deep, we would have to apply Manning's equation in a circular conduit. The reason being is that until that water surface is above the top of the outlet pipe, it's acting as an open channel. And ordinary orifice equations don't make sense in that case. And then once we get slightly bigger than 5 feet deep, up to 12 feet, we can simply apply the orifice equation directly. Then we want to save that information in a depth storage outflow table for use in building a storage indication curve, and then we'll use that to build a routing table. So let's go through the steps to do that. We can apply Manning's equation for a circular cross section, and we can repeatedly use a tool like this spreadsheet, starting with a very small depth and increasing the depth up to 5 feet with a specified slope, and calculate different outputs for the first 5 feet. So you wouldn't do it for 0 feet and then 5 feet. Maybe you do it for half a foot, 1 foot, 1.5, 2, all the way up to 5 feet deep. And that would build the first part of the table. And in this particular case, the example from Chow Mabit Mays at 5 feet of depth has 137 cubic feet per second of discharge, and here we have 143. So it's likely that in the Chow Mabit Mays example, when it was created, that there's a different slope or a different Manning's end applied to the pipe. But what is important is the order of magnitude of the result are the same, about 140 cubic feet per second for the first 5 feet of depth. Once we go beyond 5 feet deep, we now can apply an orifice calculator, and the orifice calculation for discharge is a discharge coefficient multiplied by the cross-sectional area of the orifice multiplied by the square root of 2gh, where h is the distance from the water surface to the center line of the orifice. This particular diagram is taken from Section 8 of the NHI Highway Hydrology Handbook, which is included on the server. There's similar equations for orifices, so where you choose to source the information is somewhat irrelevant. And then we can build, again, a computational support tool to allow us to put depths above the top of the orifice, in this case this distance, and it's going to compute the distance to the center line because we know what the diameter is, and it will produce the necessary added discharge. So in this particular example, we're 7 feet above the top of the orifice, which means the water depth is at 12 feet, and we get 278 cubic feet per second. And in the example in Chow May Bin Maze, they had 275 at a depth of 10 feet. So again, with possibly some different orifice coefficients in their example. But we now have sufficient information to create a depth storage outflow table. And so here is that depth outflow table for different depths, and in this case we kept track of how we estimated the values, and this is like the 5 places after the decimal point, which is irrelevant. That's ridiculous precision. So when I would apply this for subsequent work, I'd probably just round to the nearest whole number. So for example, 2.98, I would just write that as a 3 cubic feet per second. Then we can copy the depth storage outflow into a routing table, which is what we're going to build. And we're going to need it as a tabulation so that we can use index and matching techniques to pull values from the table in the R environment as opposed to Excel, which this particular example shows it done in Excel. This indexing and matching is far easier to accomplish because the interpolation can be done using the approx function. So now we have copied our storage indication curve, the outflow for different depths, and once we know the depths, we can determine the storage in cubic feet in that little basin. And we can now do 2 times S over delta T plus the outflow to produce these indication depths. And now we can construct the routing table. So we have a time index, and then we have to decide what our time step length is going to be. In this example, we're using 10 minutes, which converted into seconds. And so now we have the inflow hydrograph. Now that was provided in the example input. Here's the inflow hydrograph every 10 minutes. And so we want to route that through this detention basin. So we have the average inflow for each of the 10-minute intervals. So the average inflow at time 0, 0. At 60, I think that should be a 30. That's weird. Do I have that wrong? Nope. And then the average inflow in the next time interval is 180 300, 425, 40, and so on. So we're just following this formula. So the inflow at the current time plus the prior time. So current time's 120, prior 60, so we get a 180. Current's 180, prior's 120, so we get a 300, and so on. And then our time step length. Then we compute 2 times the current storage over time step plus the outflow in this column. And 2 times the current storage divided by the time step plus the outflow. It goes in that column. And then we perform our table lookups. And the table lookups are performed using the storage indication values and the outflow values from our depth outflow function. We find a low value, a high value, and then we interpolate between these columns. And with the interpolated values, we can supply the different parts of the formula. Perform those calculations, and when we're done, we actually have the interpolated outflow and storage. So the hydrograph routed through, see if I can, let me find the hydrograph. There we go. No, not yet. So here's our inflow hydrograph going 0 up to 360 and then back down to 0. This column right here. And when we perform the necessary arithmetic, our outflow hydrograph is starting here at essentially 0 and going up to 247 and then back down. 247 in that case occurs at row 43, so let's see when that is. So the peak of the outflow occurs 10, 20, 30, 40 minutes later than the peak of the inflow. And I believe I have a graphic showing the plot. That comes later. Okay, so in the past, we would go to the trouble to build these spreadsheets to understand the routing technique. The spreadsheet is provided on the server. God, I hesitate to go back and look, but let's see what happens. The routing example that we just looked at is right there. I'm going to open it and see if it'll work. So the triangular one is the inflow hydrograph, and the red is the outflow hydrograph. Actually, we might need this for later on in the example today. And this admittedly looks complicated, almost unnecessarily complicated. And that would be a fair critique of it. I actually agree with that this is unnecessarily complicated. All it's doing is using this outflow storage function to calculate changes in storage for each of these time increments, and then the outflow associated with those changes in storage, and then we're reporting the outflow as this red line. So in this particular 1 acre basin that can get up to 10 feet deep, our incoming peak discharge is a little over 350 cubic feet per second, and that 1 acre hole in the ground reduces that discharge to 250 cubic feet per second and delays its arrival 40 or 50 minutes. That's the essence of level pool routing. So doing it in a spreadsheet is clearly it's doable. I would argue that's probably not the not the best decision to make when we have tools like HEC HMS, which we'll manage the computations for us. That's the whole point of learning to use those tools. So see, I think I'll return there. It should be cached. Yes. So the full spreadsheet is there. It has, since I had to activate a macro, it has some sort of macro in it. You can probably look at the macro sheet and figure out what it's doing. The computations that we just illustrated are far easier to perform in HEC-HMS, or in SWIM for that matter, because it handles the building of that routing table for us. In the case of HEC-HMS, it also internally selects a decent time step. If the time step is poorly selected, if it's too big or too small for that matter, the computations are hopelessly impacted. We can also apply level pool routing for stream reach. So it doesn't have to be a reservoir. It could be a stream. And if it's a stream reach, our outflow hydraulics is a little bit more complicated, but not hopelessly. And so it's an appropriate tool for streams and reservoirs. Although generally for streams we'd use a different technique. If it's going to be a hydrologic routing, the different technique would most likely be a Muskingum-Kunj method. Everything's going wonky right now because my cat has decided to do the presentation on my behalf. There we go. Sorry about that. So let's look at some of the concepts related to a reservoir. So reservoir is a pond, lake, or basin, either natural or artificial. There's two kinds. There's regulated and unregulated. A regulated reservoir has movable gates and valves. The unregulated reservoir, that's not the case. The head and the various orifice geometries determine outflow. In the case of a regulated reservoir, the head and the valve settings, which are controllable geometry, determine the outflow. Some ways of representing storage are storage versus discharge. That information is sometimes known. Storage versus elevation, or surface area versus elevation. In HEC-HMS, that is the common way to provide information is surface area versus elevation, although you can choose to do a storage elevation representation. In terms of discharge in HEC-HMS, there's spillways and weirs, there's orifices and sluice gates. I don't think it has pumps, and I don't think it has a dam breach capability. And so what I want to do with the next few minutes that remains is build a reservoir model example. So let me save this example. File, new. That rather strange name is, God, my cat has a big paw. He was able to press 7 and 4 times before I pushed him off the keyboard. So we have that, and recall what components are necessary for a HEC-HMS model. They are a basin model, launch, a meteorological model. And control specifications model. And actually, I just looked at the time. See, it's 9:57. We're scheduled to 10:30. I'll see how far I can get in another 10 minutes. But I don't want to rush it. And undoubtedly, I'm going to encounter problems. So we're going to use the reservoir icon. And we're going to route some flows through a reservoir using level pool routing. We'll specify orifice and weir flow. So we'll use source, reservoir, and sink. So in our basin, we're going to have, see, there's a reservoir tool. So I'm going to drop a reservoir on here without thinking about where it goes. And that's my source. So what the source is it'll allow us to assign a hydrograph to that element, and then we can pass that hydrograph to some other elements. And sink. So there's our basic setup, and the source, I'm going to want to downstream it to the reservoir. There's a graphical way to do what I've just done, and I don't actually recall how to, I think you click on that and that. Nope. There we go, connect downstream. So whatever comes out of the source goes through the reservoir. Whatever comes out of the reservoir goes to the sink. So now we have established that setup. Let's return to our example. The heavy lifting is in the reservoir specification. Has to have a meteorological model, but we can set it to none. So we'll take advantage of that note. Looks like it's default set to none, so we're good there. Let's go ahead and build our inflow gauge. So we'll use the time series data manager. Create a discharge gauge, choose new. Great. We're okay there. We need to set our time step. Set time step to 10 minutes. I don't know where to do that. We'll figure that out as we proceed. See if the basin. It's got to be in control specifications. There we go. So that's all set. We'll have to do start and stop dates eventually. So now we'll set up our gauge, and I believe we're using cubic feet per second to enter our data. I guess we'll leave that time window and we will add the results. So there's our input. What we want to do now is enter our input table. Looks like we got some data in. That's somewhat different than yesterday's. And we'll just finish, we'll pad everything with 0. Fill. Repeat first value, choose OK. Hit graph. And I now believe we have our inflow hydrograph. So let me go ahead and save everything I've done so far, because that's half of the hard work right there. Our next step in the example, we have the data in, is to build our reservoir information. And that's going to be our storage discharge function. Yeah, we're going to do a storage discharge. The storage discharge information is contained right here. Storage discharge. And we want storage discharge, which I think comes under, here's a new thing. This is a paired data. Storage discharge. It almost knew what we wanted. So now we will open our storage discharge function, table 1, and we're going to have acre feet. And cubic feet. I can turn the cubic feet and acre feet within the software. And CFS is the output. Okay, so let's go ahead and see if we can build this one at a time. I'll copy that. Oh, sweet. Copy that. So discharge and storage look correct. Now we've got to turn those cubic feet into acre feet to be in the correct units. So here we're going to take it. Oh, it actually didn't paste anything correctly. Let's redo that. Copy that. Paste. Still not doing it correctly. That's nice. There we go. All right, I think that's what we wanted. Save the work. Now we want to get our, that was discharge. Now we want to get our storage term. We'll copy that. Paste it there. Paste it there. Okay, so now the only repair we have to make now is the units. This is expecting acre feet, and we've provided cubic feet. So one of the tools we can use is the fill tool. And we want to multiply by a constant. And the constant is going to be 1 divided by um, 2.2957 times 10 to the minus fifth. 2.2957 e minus 5. So that should get our storage into the correct units. I think a maximum storage, the number should be something like 12 acre feet. And it completely ignored my input. Try that again. Fill, multiply by a constant, 2.2957 e minus 0.5. Okay, let's be sure that that's actually working correctly. This equals that. So it should go up to 12 acre feet, and ours is going quite a bit beyond. That's odd. Made a mistake somewhere. I'm just going to copy and paste this. Copy that. There we go. So now we have our storage discharge table. Save that. Shrinkify that. And I don't think I need that. And we will now continue with the example. So we've provided that input. We've already made the connectivity. And detention depth, storage elevation function is also required. That's actually going to be easy. It's also paired data. We need elevation. You want a storage elevation function. Okay, so it's feet of depth, acre feet of storage. So at 0, we have 0. At 6, we have 6. At 12, we have 12. And we'll go up and add some extra. If it gets above 12, our system is wrong. There's our storage elevation function. In practice, these can be a little bit more elaborate than what I've just depicted there. I think I want to use storage discharge function. got that. Elevation method. Reservoir routes to the sink. And our source is built. And okay, so storage method, elevated storage discharge. I think I want elevation storage discharge. There we go. So we have a storage discharge function, which is table 1. We have a elevation storage function, which is also a table 1, but it's a different table. And the storage method that will be used is elevation storage discharge. So we provide two pieces of information, the depth storage information and the storage outflow information. And that's all we're providing to this basin. Our input value is the source term, and then the sink is going to receive everything. I believe I have everything set up ready to go, except for the control specifications. So we will fix that really quickly. So we need a 01 January 2000, 02 January 2000, and okay, I think we're now set to go. Let me say that. I'm going to attempt to run this simulation. And see, compute. I need to create a simulation run, set the defaults, hit finish. Run. Let's see, simulation time. Oh, please. One more try. One error. Not ascending. So, well, I'm out of time. It's giving me an error which is new to me because I'm pretty sure I have created the tables correctly. So it says elevation storage or storage discharge table are not ascending. Looks like they're getting bigger to me. If it's having issues, it might be with that little kink right there, which we can certainly fix. It's at about somewhere between 150 and around 5. Right here. So I can take that 143, I'll just make it a 153. So technically that should be ascending. Save it. Literally that was all that was wrong. Hit close, and now I want to look at my output, and then I have no output. So I have a couple more connections to make. It's 17 after the hour, and I think it would be in the best interest for me to let's see what I forgot. Oh, outflow curve. That was my bad. I do not have the reservoir. No, that's correct. So I took care of the kink. I know I have everything working right. There's no inflow coming in. So my mistake is in the source. Let's try that. Yeah. Inflow. That looks more hopeful to me. Yay! Okay, so my goal is this guy right here. So this should plot the inflow and the outflow hydrograph. And it does. And it does. Resize it. So the triangular is the inflow hydrograph. And here's the outflow hydrograph that's computed. And I argue that that was actually a whole lot simpler than building a computer spreadsheet to accomplish the same task. And if the spreadsheet will come back to life. So there's the spreadsheet in the Heck HMS version, and they're quite similar. I would argue they're not. I doubt they're identical, but they're really close because they're using the same methodology. And providing those two columns as well as a depth storage pair of data is far simpler than constructing this elaborate spreadsheet and doing the calculations yourself. So at this point, my statement would be Heck HMS is the preferred tool for doing level pool routing. That concludes what I wanted to accomplish today. I want to thank you all for your patience as we're working through network issues and things breaking beyond my control. And I'm making the repairs, and we will proceed accordingly. In the meantime, have a good afternoon. Are there any questions? Well, if there's no questions, I'm going to go ahead and terminate the meeting, render the video, and get it uploaded, and continue repairing the server so that you all have access to the pieces that you used to have access to. If there's no further questions, then I will go ahead and end the meeting for today. Thank you for your time. I'll see you tomorrow.